All right, section 3.6, we're going to look at word problems and how we create functions to find the answers to these questions. So here, our first example, it says, let f of x equal x squared. There's our basic parabola right here on our graph. Find a function a of x for the area of the shaded triangle where the first corner must stay at the origin, 0, 0. The second corner has to be on the y-axis, 0, y. And the third point is located somewhere on the function in quadrant 1. So this means that this point can move anywhere on the function. If we slide it down to here, based on this point, where the x is at, we want to know what the area of this right triangle is. If we slide it down further, the area is getting smaller. All right? So our goal here is to come up with a formula for the area of our triangle, which is 1/2 times base times height. But whatever we multiply together has to be written in terms of x. It can only have the variable x in it. So that's our goal here. So looking at my base from 0y to xy, that's a distance of x, whatever the x coordinate is. So that's your base. Your height is from 0 up to y, but we can't put y in there. So looking at the equation of our function, f of x equals x squared, is the same as saying y equals x squared. We're going to put that in for the height. So we have 1/2 times x, the base, times x squared, the height, which is 1/2 x cubed. So this is a function based on x to find the area of this triangle, which is going to be a right triangle. And the only value you need to know is the x coordinate located on the parabola will tell you the area of the right triangle that's created. All right. Next example. Here we have a semicircle with a rectangle inside the semicircle. So we're going to represent our entire semicircle. Think of it as a whole circle centered at the origin, and has a radius of 6 to the right, 6 to the left, 6 up. That's the equation of a circle. X squared plus y squared equals 36. Now, we're going to let our point be anywhere we want on this semicircle. And again, we want to find the area of the rectangle based only upon the x coordinate. So again, our area formula for a rectangle is length times width, or base times height. So my base is the whole entire bottom of my rectangle. Here's my height. So to rewrite my function, our base written in terms of x, let's do base first. Well, from 0 out to this point x here, that's x, but that's only half the base. So we're flipping over the y-axis to this point. So there's technically 2x's here. So my entire base is 2x units long, and I'm going to need to put absolute value bars around it, because what if the x, y point we choose is over in quadrant 2, giving us a negative x value? And you can't put a negative x in for a distance. It has to be positive, so putting absolute value bars guarantees no matter where the x is located, it's going to be a positive value. So my height is the y coordinate, but I can't put y in my formula. It can only have an x. So I need to look at another equation that has x and y in it, and that's my circle equation up here. We need to take that equation and solve it for y. I know what you're thinking. You told me earlier y is to an even power. This is not a function. I can't solve it for y. Well, I really didn't say you can't solve it for y. I just said it would be ugly. So we can't solve this for y. We'd subtract over the x squared, and to undo the power of 2, you take the square root. And you're thinking, well, that's not so bad, but it has to be a plus or minus, positive or negative square root when you solve this. And that's why we can't do that for functions. We would have y equals to 2 different equations. And therefore, it's not a function. But because our semicircle is completely above the x-axis, which means our y's will always be positive, we'll leave it as a positive square root of 36 minus x squared, and we'll change that and put it in for the y. And there's my function for finding the area of the rectangle inside the semicircle, completely based on the x-coordinate of the point anywhere on the semicircle. Now, if you were asked a question like, okay, what x-coordinate in quadrant 1 will maximize the area? Okay, so if we're going to do this in quadrant 1 only, well, then the x is guaranteed to be positive, and we don't need the absolute value bars here. So I'm going to go grab my calculator, and I'm going to go to y. Whoops, don't change my calculator that much. I'm going to change my y1 to 2x times second square root 36 minus x squared. Enter. There's my function. Now, let's talk about the window that we want. Okay, we said we're only going to be in quadrant 1, so that's 0 to 6 for your x's. So window, let's change that from 0 to 6. Y value, okay, my area, the biggest I could possibly even think about having would be, let's say, a 6 by 6, and that's bigger than big. That's way too big. But it'd be a good Y max for us, so we could say 36 or 35. Those would be all good. So our Y min would be from 0. And if you want to leave this as 30 from when we used it before, that should be a pretty good choice. If you want to change it to 36 to be on the safe side, so be it. I'll leave it at 30. And I graph it. Whoops, I guess I need more y's there. Oh, I know what I forgot to do. It's what I forgot. I got to think about the area on this side too, so we better double that 30 to maybe 60. So let's try 60, regraph it. Okay, that's better. Now I see the whole graph. And I can see in my graph there's definitely going to be a relative max somewhere in this area. 1, 2, 3, definitely between 3 and 5. Not quite sure about 4, but definitely between 3 and 5. So second trace, ask for the max, number 4. Left bound, 3 is good, just hit enter. Let's type in 5, enter, and there's that high point somewhere between our two triangles or those straight lines. And then just hit enter on guess, and the x coordinate you need is 4.242673. That's the x coordinate that's going to give you the biggest maximum area of that rectangle of 36 square units. Okay? All right, next example. It's a classic problem. An island is 2 miles from the nearest point P on a straight shoreline. So here's my island I to the point P. You might want to call it a pier or something like that on the shoreline, 2 miles apart. Now, from this point P down to the town to the right, due east if you will, is 12 miles apart. If a person can row a boat an average speed of 3 miles per hour, and the same person can walk an average speed of 5 miles per hour, we want to write a model that expresses the time, capital T, that it takes to go from the island to the town as a function of the distance x away from point P. Okay, so what they're saying here is that sure, you can row your boat straight to the shore and then you walk. All right, what they're saying is that there's going to be some point between P and T where that will make your time lower, the minimum amount of time to travel. All right, so what we need to do is to write our function t as a function of x. So that's t of x, capital T of x equals. Now, we got to find the time it takes to row your boat to somewhere on the shore. Well, we don't want to just row right to town because rowing is only 3 miles per hour. That's a slow rate. And so that's going to probably be the longest thing to do. All right. And then we want to find the time walking. So from this point somewhere in between P and T to here, that's when we want to walk into town at 5 miles per hour. So let's take care of rowing. We need our distance equals rate times time formula because it has distance in it, rate, and time. We're going to solve it for t by dividing over the r. So we need to write our time for rowing and our time for walking as the distance we traveled rowing over the rowing rate and the distance we walk over the rate at which we walk. So let's attack the rowing time. We have a right triangle here. So I know that the rate of rowing is 3 miles, so we can put that in. We have to find the distance of this hypotenuse of this right triangle. So I'm going to use the Pythagorean Theorem. X squared plus 2 squared is going to equal capital D squared. All right, so 2 squared is 4 plus x squared. Then take the square root of both sides to get capital D by itself. And I'm going to substitute that in for this D right here. And this is the expression for my rowing time, distance over rate. That's the time for rowing. Now, time for walking is this distance right here. Well, it's not labeled. I need to put something there. But again, we know how fast we walk is 5 miles per hour. So just like we did with the rowing time, let's put 5 in for R and then find the distance we need to walk. Well, from P to T is 12 miles. If we subtract off the X miles from where we land our boat, we have 12 minus X miles to walk. So that's your distance. We'll put that in right there. So now my T of X, I have the rowing time expression. I have the walking time expression. There's my function for T of X. So of course, just like the last problem where they asked us what point in quadrant 1 would get you the maximum area of the rectangle, they're going to probably ask you what value for x will give you the least amount of time traveled to the town. So what is the fastest time to go from the island to town? Again, take your function, type it into y1. Again, you can use that alpha y equals at fraction shortcut to type it in, plug it in, graph it. Again, talk about your window for your x's. We're going to go from 0 to 12 for your domain. All right. My largest possible y, well, let's see. If x were to equal 12, this is gone. All right. This would be 4 plus 12 squared. Okay, that's just 12. Just a little bit bigger than 12. Or excuse me, 4. Wait, let me back up. A little bit bigger than 12 divided by 3, which is 4. That's what I wanted to say. So call it 5. Y min, well, let's call it -1, or we can call it 0. So we made the graph. Remember, in the old 83s, we want to get the x-axis off of the bottom of the screen. So we have what looks to be what looks like a really wide parabola here. It starts out here, drops down for a little bit, and starts heading back up. So if we do our min value, say left bound from 0, let's say right bound about 5, that's about out to here, that's good. And and enter on the guess, your minimum is at about 1.5, probably a slight rounding error here. So we'll just call it 1.5 miles from point P. It's going to take you 2.933. Well, remember, your rate was in miles per hour. It's going to be almost 3 hours, just under 3 hours to get to town if you land your boat 1.5 miles away from point P. Next example here, we have an open box with a square base is to be made from a square piece of cardboard, 36 inches on each side, by cutting out a square from each corner and turning up the sides. Find a function for the volume of the box. Okay, so the volume of a box is length times width times height. Length, width, height. So what we know here is that all 3 of these dimensions have to be written with a variable x in it. Okay, well, what I know right now is that this is 36 by 36 piece of cardboard. What they didn't tell me was how big of a square from each corner I'm going to cut out. So that's going to be my x. This is going to be x by x, x by x, x by x, x by x. So now if I cut that out and I fold this up, that means the height of my box is x. So that's the height. The length and the width are these dotted lines right here, the bottom of my box. Well, let's see, how are we going to find those values? Well, let's see, it's 36 inches this way, and then I chop off an x and I chop off another x, so that's taking off 2 x's, so each of these 2 bottom sides, because this is 36 and this is 36, length and width 36 because it's a square piece of cardboard, will be 36 minus 2x. So base is 36 minus 2x, width is 36 minus 2x, height x. So this is the binomial 36 minus 2x squared times an x. What x by x squared do you need to cut out of the box or out of the cardboard to generate maximum volume? All right, we're going to go to y equals, and we're going to put that into y1. But first, we got to figure out what is going to be my domain. What's my x min and my x max? Well, we could cut out a 0 by 0 square. And then the biggest x you can cut out is you really can't go anywhere past halfway. Half of 36 is 18. So my x min and my x max is going to be actually boxes that don't exist. 0 by 0, it's still a flat piece of cardboard. If I cut it and make it 18.5, I just cut it into 4 equal pieces. So we're definitely going to find our max between those two values. Now, what's going to be my maximum y? Well, honestly, I just guessed numbers. Okay? So I figured, well, let's see. It's probably going to be somewhere in between here. And I think what I did is I said, let's just round some numbers here to keep it easy. Square the number, multiply it by it again, and you can pick, I think I picked something like maybe 20 or something, or not 20 because it's bigger than 18. A 10 is 100 times another 10, 1,000. So I said, well, it could possibly be bigger based on how much, so multiplied it by 5. You know, if they, again, like we saw earlier, if your graph doesn't fit, then you just change your graph. So I graphed it. There's my high point. Everything looks good. I found the max again. All right. Somewhere to the left, somewhere to the right, left bound, right bound. Hit enter on guess. And we got 5.999984. Well, wait a minute. I can't put this number in here and expect to get a maximum volume that's a complete integer. So this is probably a rounding error. So if you go to the trace mode, you type in a 6 to see if you get the same 3456, which I did, then 6 is my x. So that is the size of the square I want to cut out from each corner, which will give me the maximum volume for that box. Okay? And that's 3.6.